Thank you everyone for being here for my master's defense presentation titled Seismic Attribute Analyses and Attenuation Applications for gas hydrate or for detecting gas hydrate presence. My name is Roberto Clement and my committee members include Dr. Heather Beadle, Dr. Kurt Marford and Dr. Yishuan Wang. Okay. So just a brief overview. First, we'll get into the introduction. I'll have to change this because, okay. First, we'll get into an introduction about what gas hydrates are and why they're important. Then we get into the motivation and objectives of this study. Then look at the study area that this study is being conducted. Then we'll get into the methodologies used, the results of those methodologies, and we'll end with a conclusion and future work section. So what are gas hydrates? Gas hydrates are naturally occurring methane gas trapped within a crystalline lattice of hydrogen bonded water molecules. Why do we care about gas hydrates? Well, methane serves as a potential energy resource, and since it is the most simplest hydrocarbon compound, it is also a cleaner natural resource. Additionally, gas hydrates serve as potential geohazards because of natural or man-made events such as drilling that can result in destabilization as pressure changes occurs with the gas hydrates and surrounding sediments, which will result in potential land failure such as landslides. This, of course, can affect industrial operations. The conditions for gas hydrates or the formation conditions include their formation within low temperature and high pressure conditions in locations beneath the permafrost, as well as shallow subsurface in deep water continental sediments. Gas hydrates form between what is known as the gas hydrate stability zone. As shown in this phase diagram taken from Ruppel and Kessler 2017, it shows the interval of the gas hydrates between the seafloor and the point at which the geotherm intersects a methane hydrate equilibrium curve. The bottom of this interval is represented in seismic data as what we call a BSR or bottom simulating reflector. As aforementioned, the way to detect gas hydrates in the subsurface, or one of the most traditional ways using seismic data, is via a bottom simulating reflector. Bottom simulating reflectors have an opposite polarity response to that of the seabed, as well as it mimics the trend of the seafloor and also cross-cut stratigraphic layers. These are a few of the ways that we can detect bottom simulating reflectors in seismic data. Additionally, bottom simulating reflectors represent the transition from hydrate-bearing sediments to free gas-bearing sediments below, and this change in medium properties can incite an attenuation response responsible for the reflection or responsible for the bottom simulator reflection in the seismic data. However, this isn't always a consistent relationship to detect gas hydrates in the subsurface or when using seismic data. Since bottom simulating reflectors do not always equal gas hydrate presence, neither do no bottom simulating reflectors or lack of bottom simulating reflectors indicate no gas hydrate presence. And that's the conundrum. So our motivation for the study, or my motivation for the study, is to improve the detection of gas hydrates and bottom simulating reflectors, and particularly the gas hydrate systems as a whole, using a attenuation method. Attenuation can be described as the decay of energy of a propagating wave due to factors of geometrical spreading, scattering, and absorption of wave particles with particular sediment particles in the subsurface. Just a representation of, and here's a representation of how high frequency signals attenuate much faster than low frequency signals, even at similar distances. And this will make a lot more sense as we go along with the presentation. Overall, attenuation is an important tool for identifying pore structure, lithology differences, and even changes in fluid content, such as gas versus solids or water or liquid. So we have several objectives objectives for this study. Our first objective is to improve the detection of bottom simulating reflectors in seismic data. Then we would like to measure and estimate the attenuation response of hydrate systems in regions that include strong continuous bottom simulating reflectors, weak or discontinuous bottom simulating reflectors, and very strong continuous bottom simulating reflectors. Then we would like to compare the results of the direct attenuation method to traditional attributes that have been used to identify bottom simulating reflectors and gas hydrates in the subsurface of the frequency kind. We will also improve the detection when comparing it to the traditional frequency attributes using a spectral decomposition method. Our next objective is we would like to better infer free gas distribution and accumulation in addition to hydrates using this attenuation method. Then we would like to determine whether this attenuation method can be applied to other areas of interest where gas hydrates have been known to gas hydrates have been inferred to be found, such as in the Gulf of Mexico, and we will show that later on in this presentation. So the study area for this application is located in the Pegasus Basin, which is on the eastern side of the central New Zealand mid-continent, adjacent to the tectonic transition zone that defines the subduction of the Pacific plate beneath the overriding Australian plate. The basin underwent over 80 million years of passive margin-style sedimentation as a result of rift-related thermal subsidence, which was then accumulated by an 8-kilometer thick succession of siliclastic material, most that was sourced from the structural height of the Chatham Rise. We focus our application using the PEG-09 or 2009 acquired PEG-09 survey, which is a 2D multi-channel survey, as well as a more recent 2013 APB13 survey, which consists of higher resolution seismic data when compared to the PEG-09 data. Here is a cross-section of the PEG-09-19 seismic line that shows 3 bathymetric areas of interest where gas hydrate systems have been known to be located within the subsurface. They include the Upper Bank, the frontal anticline, and the Hikurungu Channel. We focus our studies on Zone A, which include the strong continuous BSR in addition to the frontal anticline, Zone B, which includes the weak discontinuous BSR, and Zone C, which includes the very strong continuous BSR. Previous studies of gas hydrates within the Pegasus Basin has constrained gas hydrates to be located within an interval of Pleistocene age sediments. Together, this study by Plaza et al. Also shows a conceptual diagram that shows these 3 bathymetric areas of interest and the associated gas hydrate systems that exist. They interpret the bottom simulating reflector, methane recycling between the methane hydrate stability zone and the free gas beneath. They interpret in situ gas hydrates that are located within the gas hydrate stability zone, as well as fluid migration paths through faults beneath the frontal anticline, faults beneath the upper bank, and also along the subduction zone and through stratigraphic layers accumulating near the Hikurungu Channel. They also represent these gas bubbles to show the accumulation of free gas in these areas of interest. For this study, we focus on this green boundary that encompasses the frontal anticline and the Hikurungu Channel, focusing on gas hydrate systems near these areas of interest. Additionally, a study by Kruger et al. 2015 uses thermal modeling to show the migration and accumulation of free gas through the subduction and through faults and fractures, as well as stratigraphic layers that accumulate in the frontal anticline region, as well as in the Hikurungu Channel and areas west of the Hikurungu Channel. The study encompasses a very simple workflow. First, we use the Pegasus 09 data to apply seismic attributes that involve attributes of the frequency kind, specifically instantaneous frequency and sweetness. Then we apply a spectral decomposition method, the continuous wavelet transform. Then we use both the PEG-09 and APB13 surveys to apply the attenuation method as suggested, called sparse spike decomposition. And then we apply that attenuation method to a couple surveys in the Gulf of Mexico, specifically near the Green Canyon and Alaminos Canyon. Then we interpret and analyze all of the results. So we use three methods for this study. Our first method is an attribute analysis that involves attributes of the frequency kind. We use an instantaneous frequency, which is derived from complex trace analysis of a seismic trace to help better resolve the bottom simulating reflector in the seismic data, and also use it as a way of indirectly inferring free gas accumulation based on attenuation responses. We also use the sweetness attribute, which is described as the envelope of the seismic trace divided by the instantaneous frequency squared, to better resolve the trend of the bottom simulating reflector. Our second method involves the spectral decomposition method, known as continuous wavelet transform, which allows us to convert our data from the time domain to frequency domain. This continuous wavelet transform is described as a convolution of Morlet wavelets with the seismic trace to provide individual wavelets at various frequencies for us, which basically describes the decomposition method that is being applied. This way we can observe the data at different frequency responses. We pay a particular attention to a parameter known as the half bandwidth, which influences the size of the Morlet wavelet, or the shape of the Morlet wavelet, which convolves with the signal, and therefore influencing or affecting the size can allow in changes in the resolution of the data. Therefore, we use the best half-width parameter to compute our individual frequency components. The last method, which is the attenuation method known as sparse spike decomposition, developed by Wang and Morrisov 2020, allows us to directly measure the attenuation response using an attenuation parameter known as the quality Q factor. Generally, this method allows us to estimate a wavelet from the seismic trace, sort of similar to how the Morlet wavelet is described. And using this estimated wavelet, we can calculate the quality factor to measure the attenuation response directly. The benefit of this method is that it requires no well logs and usually uses only seismic data. On to the results. For our attribute analyses, the instantaneous frequency shows a low to mid frequency response where we interpret the strong continuous BSR. For the weak discontinuous BSR, we observe no frequency response, or a response that is too familiar with the background geology, and therefore it's difficult to distinguish the response from the background geology. And we also interpret a low to mid frequency response in the region of the very strong continuous BSR. Additionally, we interpret a feature known as a low frequency shadow zone, which is a result of the decay of energy of the propagating wave due to the accumulation of free gas, which will attenuate the seismic signal, resulting in this low frequency shadow zone. We therefore interpret the accumulation of free gas from the faults and fractures as interpreted in previous studies that exist beneath this anticlinal feature, where the crest of the domain anticline will most likely act as a seal to the accumulation and migration of the free gas. We also observe a low frequency shadow zone in the area beneath the very strong continuous BSR, again associated with the potential migration and accumulation of free gas, most likely derived from the subduction zone as previously interpreted, where free gas most likely migrated upward. Again, it is difficult to distinguish the response of the instantaneous frequency to that of the background geology response. However, the sweetness attribute clearly distinguishes the trend of the bottom simulating reflector from that of the background geology, such that the strong continuous BSRs are associated with high sweetness responses. The weak discontinuous BSR sort of has a poor to medium response, but however, we can still somewhat identify the trend of the bottom simulating reflector. Again, for the very strong BSR, we also have a very strong response in the sweetness attributes. And these strong sweetness responses can correlate or infer the accumulation of free gas beneath the crest of this anticline, or this sealed portion of the anticline, and beneath the very strong continuous BSR. Unfortunately, the sweetness attribute does not allow us to interpret the low frequency shadow zone future, and therefore this attribute can be misleading to geophysicists or interpreters hoping to interpret the presence of free gas in such areas. As mentioned, we chose several different half bandwidths for computing our spectral components or spectral decomposition components. We use a half bandwidth of 0.52, which gives us better resolution in frequency and time, as compared to 0.26, which gives us poor temporal variation, and the half bandwidth of 0.78 is too smoothened in the frequency axis. Therefore, out of all the options, we choose the half bandwidth of 0.52 for our spectral components. So here are the results of the spectrally decomposed components for 20 Hertz, 40 Hertz, 60 Hertz, and 80 Hertz components. In each case, we can observe that the strong continuous BSRs have high magnitude responses, as well as the very strong continuous BSRs. However, the weak discontinuous BSRs are not as distinguished from the background geology, and therefore can show the one of the weaknesses of this method as well. What we observe in the larger frequency components are the trends of the bottom simulating reflectors, together with the low frequency shadow zone, which describes, or which basically informs us that based on the high attenuation of the signal, or the high frequency of the signal, it attenuates much faster. Hence, using these high frequency components, we are able to better resolve the low frequency shadow zone because of the decay of energy caused by or influenced by the free gas accumulation. Overall, we observe that the continuous wavelet transform, or the spectral decomposition method, allows us to better resolve the bottom simulating reflector, in addition to resolving the low frequency shadow zone, as compared to the sweetness attribute, where we weren't able to resolve the low frequency shadow zone, and with the instantaneous frequency, where the reflection strength wasn't as strong as compared to what we observe on the spectral decomposition application. Now on to the results for the attenuation application. And we focus here, or we compare the results of the PEGO 9-19 survey to that of the APB 13-40 survey lines. And we compare the strong continuous BSR, the weak discontinuous BSR, as well as the very strong continuous BSR. It is also worth mentioning that using the APB 13 survey, which has a higher resolution, we're better able to interpret a fault that lies beneath the frontal anticline feature, as compared to the PEGO 9-19 survey, which we cannot resolve this fault. And it is important to indicate this, that to support the idea for migration of gas up to the fault to accumulate beneath this area of interest. Again, to remind the audience of where we are located in terms of the seismic lines and our comparisons of zone A for each line, zone B, and zone C. So our results for the attenuation seem very promising. We observed that in the area of the strong continuous BSR, we see a significant attenuation response that has a large distribution with depth, or a somewhat significant distribution with depth below the BSR. In the regions of the non-visible BSR, we don't observe any attenuation. Additionally, we observe a high concentration of attenuation within the areas of the anticlinal future. again suggesting a likely accumulation and presence of free gas that would have migrated up through the flanks of the or the crest of the flanks of the anticline feature along the flanks, as well as we observe a high attenuation in the APB13 survey directly beneath the anticline crest, which would support the presence of free gas that would migrate up through the faults located beneath the anticline. And also it co-locates with our interpretations of the low frequency shadow zone associated with attenuation that we observed in our instantaneous frequency and and our spectrally decomposition results. When observing the non-visible BSR, we observe an attenuation response at depth and not significantly, or not directly rather, beneath the interpreted trend of the bottom simulating reflector. Previous studies have shown that the fine-grained sediments within this region can likely act as can likely provide low porosity and permeability, together with the lack of migration pathways such as faults, would not allow for the accumulation or migration and accumulation of free gas towards the surface. Therefore, no attenuation response is observed where we interpret the trend of the BSR or directly beneath the trend of the BSR. However, in the region of the very strong continuous BSR, we observe the largest attenuation responses in the seismic data, especially beneath the area of the, or especially within where we interpret the accumulation and presence of free gas, as shown in the previous studies that are located near the Hikurungu channel. We observe that this high attenuation can be as a result of the migration of free gas that derived from the subduction or along the subduction zone. It is also likely that based on the previous studies that suggest that the sediments located closer to the Hikurungu channel or in the region of the Hikurungu channel are much coarser grain, which would therefore allow for high porosity and potentially higher permeability, therefore allowing for a higher accumulation and presence, or higher migration and accumulation of free gas in this region. We also observe a high attenuation response directly below the seabed, which we interpret as a potential weathering zone. However, this weathering zone, or this response rather, is not observed in the APB13 survey, even though they are located several kilometers away from each other. It's sort of difficult to suggest whether this is a weathering zone or maybe a computational error. So on to our results for the other seismic surveys. We observe we apply our methods to surveys in the Alaminos Canyon and the Green Canyon survey, or locations. So here's a study done by Haynes et al. 2017 that characterizes a gas hydrate and free gas reservoir in the Green Canyon location. And for their study, they use the same 2D seismic data set that we'll be using. In addition, they use 3D seismic and well logs to interpret gas hydrates along a GC955-H well, which is supported together with core data, as well as they infer free gas and gas hydrates in the reservoir between the area of the top of the reservoir interval and also where the inferred bottom simulating reflector, which represents the base of the gas hydrate zone, they infer free gas and gas hydrates within that interval. However, they did not clearly distinguish the areas within or the zones within the reservoir that consist of free gas or gas hydrates. So for our attenuation application, we use the seismic data along seismic line 255A, and we use similar interpretations from Haynes et al. 2017 that includes these faults, the reservoir body, as well as the wells. We observe a high attenuation response in the uppermost section of the reservoir, most likely associated with the free gas accumulation. Again, they do a poor job in distinguishing within the body of the reservoir where free gas and hydrate presence occur. However, we would assume that based on the attenuation responses we have observed in the previous studies, that these attenuation responses correlate with free gas migration that would have migrated and accumulated at the top of the reservoir, are most likely sealed by this interpreted low permeability unit. As also, they interpret gas hydrate presence along the GC955-H well. However, in our attenuation application, we don't observe any attenuation response associated with the gas hydrate presence. Additionally, we observe a large attenuation zone towards the subsurface bounded by this blue polygon, which is most likely associated with free gas that migrated through certain faults in the area. Along this line, we observe that these two faults do not penetrate the main reservoir. However, several other lines do suggest that in areas close in proximity to the GC955-H well, that several faults penetrate the main body of the reservoir towards the surface, and therefore can act as migration pathways. However, this large distribution of attenuation does raise some concern, and I think it needs to be better constrained for future studies. Additionally, we examine a subtle BSR along the line, along Alaminos Canyon line WT-02. And so we show here a zoomed in image of the BSR with the yellow arrows or the yellow block arrows, and we can observe this BSR along the seismic line. However, in the attenuation response, we observe a sort of or no significant attenuation along this line. However, as we continue on the right of this interpreted fault, where we observe the low or non-visible BSR response, we can see a significant high attenuation response that encompasses this, this non-visible BSR. It is likely that the free gas migration could have occurred upward through the fault and collected on the right side of this fault, which would be associated with the attenuation response observed. So in conclusion, we have several answers to our objectives. We observe that the sweetness attribute and spectral decomposition method improves the BSR detection compared to instantaneous frequency, especially where the sweetness attribute helps improve the trend of the weak discontinuous BSR as it distinguishes its trend from the background geology. We also observe that the attenuation method does not provide a direct relationship to gas hydrate presence. However, gas hydrates can be inferred indirectly because of the attenuation response associated with free gas, specifically in the regions that encompass the strong continuous BSR and the very strong continuous BSRs. Third, the attributes and the CWT or spectral decomposition method correlates well with attenuation such that, or the attenuation method, such that there's a strong relationship between the low frequency shadow zone features that we've interpreted and high attenuation, especially beneath the strong reflections or the strong bottom simulating reflectors. We can also make inferences on the free gas migration and accumulation from attenuation, strongly supported by the previous interpretations of the region, for example, Plaza et al., where they interpret the locations of free gas accumulation as well as gas hydrates. Finally, the application to other areas of interest seem promising. However, I believe that more constraints on the subsurface features are necessary to implement a more robust approach when using this method. Finally, I show here a pros and cons summary of the methods used for this study. As a direct gas hydrate indicator, we observe that instantaneous frequency, sweetness, and continuous wave transform does poorly. However, the sparse spike decomposition or the attenuation method can indirectly infer the presence of gas hydrates due to the free gas accumulation that we observe from the high attenuation. As a free gas indicator, the instantaneous frequency and continuous Wavett transform or spectral decomposition method does well or can infer the response or the accumulation of free gas via the low frequency shadow zone features, whereas the attenuation method shows high attenuation associated with the free gas accumulation. In terms of discerning strong bottom simulating reflectors, we observe low to medium responses using the instantaneous frequency, high responses using the sweetness attribute, as well as high magnitudes when using the spectral decomposition method. We also observe high attenuation in most cases when surrounding the location of the strong continuous BSRs. With respect to the weak BSRs, we observe a poor instantaneous frequency response, poor to low sweetness responses, and poor CWT or spectral decomposition magnitudes when comparing it to the background geology or the results of the background geology. With respect to the sparse spike decomposition, it seems to vary since we observe in the Alaminos Canyon that the region of the weak or non-visible BSR had a high or significant attenuation response. Future work for this study, I think, would involve or would require an in-depth analysis of the lithology and geology or the geology and how it affects the attenuation response of the method. Exploring how the attenuation measurements are influenced by the seismic data parameters, for example, dominant frequencies or the dominant frequency of the seismic data, and also compare the seismic attenuation results to other available data such as core, well logs, and even vertical seismic profile, to name a few. Here are the references. And I would like to thank Dr. Beadle for giving me the opportunity to work with her from 2018. It's definitely been such a great time, and I appreciate her allowing me to be an independent researcher and also giving me the room to explore all of the different ideas that I've had. Thank you very much. There's a lot of things I can say, of course. Keep it simple. I'd like to thank Dr. Wang, or Yishwan, as everyone knows him as, for allowing me to work with this, with his application, his attenuation application, and also putting up with my questions for the last few months to a year. As well as Dr. Marford. I'd like to thank Dr. Marford for allowing me to be part of the ASPE family and giving me the chance to as an international student to come here and as an international student to come into grad school and do the best that I can. I'd also like to thank Jake Walter as an honorary person because back in 2018, I had the opportunity to work under him in Oklahoma Geological Survey as a summer intern. And it was then I sort of realized that I wanted to get into research, doing a couple of projects with him, or one project in particular. But my experience with him definitely made me want to pursue research and get into academia. I also like to thank my friend and mentor, Fola, for helping me become a better researcher within the last almost 2 years, and just being a good listener and person who has helped me a lot in many other ways other than academia. Thank you very much. I also like to thank everyone, the whole SDA family, all the friends that the friends and all the great relationships I've had for the last few years, also including my undergraduate years. Thank you, everyone. I also like to thank my family and close ones. Of course, I can put 1,000 pictures here, but I want to keep it simple. I especially want to thank my mother, my father, my king and my queen for everything that they've done for me, for supporting me through everything. Again, I can say so much, but I'll keep it simple. But thank you to them. And I would like to thank myself for just being who I am and all of the hard work that I've put in. And I think it's always good. People don't recognize that. You need to pat yourself on the back, and I'd like to do that for me. And and where I am today and what I've been able to accomplish. So I like to thank myself. And thank you everyone for listening to 35 minutes of my work.